Hello everyone, my name is Benjamin Lee. I'm a PhD candidate at Monash University in Melbourne, Australia, and I'll be presenting our work on the design space for data visualization transformations between 2D and 3D in mixed reality environments. In immersive analytics, it's common to conjure up ideas of people interacting with data in a fully three-dimensional space. While this is certainly compelling, using flat surfaces and screens to display conventional two-dimensional visualizations still has tremendous value. We are, of course, not the only ones to realize this. Much related work has combined screens and immersive headsets to allow for both 2D and 3D visualization simultaneously. However, these works typically either treat the 2D surface and 3D space as two distinct environments, or use the surface primarily as an input device to control the 3D visualizations. Instead, we were interested in how a visualization itself can seamlessly move between the two display environments, rather than being confined to one or the other. Which takes us to the core premise of this work. What you see here is an example of a technique on the HoloLens 2, which transforms a 2D visualization on a flat surface into 3D using a pinch and drag gesture, revealing the points which are overplotted on a scatter plot. Techniques such as these can dynamically transform visualizations between 2 and 3D to perform a specific task, leveraging both the surfaces and the space enabled by immersive headsets. There is precedent for using 3D to augment data analysis tasks on 2D screens. For instance, scatter dice and graph dice use 3D to maintain transition awareness when navigating sploms and networks. To the best of our knowledge, however, no work has yet formalized nor systematically explored the design of these transformations, particularly in immersive environments. Therefore, we contribute a design space which acts as a foundation for the creation of visualization transformations between 2 and 3D. As these transformations are basically transitions between two states, we first needed to determine what these states even are. We settled on the following 2x2 matrix, with dimensionality on one axis and multiplicity on the other. For now, we set aside the notion of surfaces and spaces to strictly focus on how the visualization encodes data, accommodating for multiple views. We then considered the purpose of these transformations. We mapped out 14 generic visualization tasks associated with the different state transitions. As an example, the overplotting technique shown earlier is an example of revealing a property of the data, going from a single 2D to 3D visualization. Note that many common visualization tasks are intentionally excluded due to their incompatibility. With this, we now have a starting point for identifying opportunities in which visualization transformations may be useful. We now can consider how an immersive analytics system designer may design these transformations for themselves. To do so, we crafted a task-driven design space based around the states of the visualization before and after the transformation, how the transformation is performed by the user, and how the transformation itself behaves. Let's break down this design space through the lens of another example technique, finding the shortest path between two nodes on a network, a very common task. Referring back to our task mapping, as we want to reveal a property of the data, this will be a single 2D to 3D transformation. The start and end states correspond with the initial and final visualization states in the design space. In a practical sense, the initial state can be thought of as a set of criteria that the visualization needs to be in order for the user to be able to use it, with the final state being the outcome of the transformation. Within these, we need to consider both the visualization schema and geometric state. The schema is how the visualization itself maps data to graphics, including its dimensionality, multiplicity, and any other particular visual encodings that may be required. For our shortest path example, this is simply a single view 2D network. The geometric state is the geometric properties of a visualization as an object in the immersive environment. Pose refers to its position, rotation, and scale, which may be relevant if, for example, the visualization needs to be in a specific position or size. We also consider what relation the visualization has with other surfaces in the environment, if it's either attached to a surface, colliding through it, or maybe just completely separate from it. In our shortest path example, we require it to be attached to a surface in order to better leverage the metaphor of data being extruded out from the surface into 3D. The user interaction section focuses on how the user interacts with the visualization to trigger the transformation. First, the interaction technique needs to be decided. This includes the input modality, which should be obvious, and the interaction target. This is the part or parts of the visualization or environment that is interacted with to trigger the transformation. Depending on the chosen technique, we can then derive values which serve as input parameters for our transformation. These can be geometric values, such as the distance between any 2 points of interest, or targeted values derived from the interaction technique. Coming back to our shortest path example, we can use mirror interaction, whereby the user selects 2 nodes with both hands. These 2 nodes will then be used as the targeted values to calculate our shortest path. To visually represent this shortest path, we'll extrude the nodes into 3D, using the distance between the user's hands and the surface to act as a scaling mechanism. Lastly, we consider how the transformation itself progresses, which progressively updates the visualization at intermediary stages. As there is an incredibly large variety of visualization and data types, we choose to take a high-level approach in order to generalize as best as possible. We consider several aspects here. First, the task that the transformation is intended to perform. In our example, it is to reveal a data property. Second, function denotes whether the transformation visually updates in a continuous or staged fashion. As we simply want to show a shortest path, we don't need to use any staging. Third, duration is how long the transformation lasts for. It can either be controlled by the user, with the transformation ending when they stop interacting, or be a fixed duration. We consider this in the context of persistence. When the transformation finishes, the visualization can either remain at its final state, or reset back to its initial state. To keep things simple, however, we will have the transformation be permanent here, with it lasting for as long as the user grabs hold of the 2 nodes. This culminates into our final complete transformation, as you see here. The network goes from 2D to 3D, with the targeted nodes being used to compute the shortest path in real time. That was a very high-level example of how the design space can be used. In addition, we contribute 7 more example techniques, which illustrate the breadth of the design space. For example, we can project a 3D scatterplot down onto a 2D surface based off the user's viewing angle. Or we can partition a 3D bar chart into several facets to view each one independently on a surface. The open source Unity project files can be found in the GitHub repository, along with a link to the supplementary video which explains each of these techniques in detail. In conclusion, we chiefly contribute a design space for the creation of visualization transformations between 2D and 3D using surfaces and spaces in the immersive analytics environments. This design space considers several more factors than other works, including such as the relevance of geometric properties in transformations, how user input can affect the transformation, and the use of ephemeral style transformations, which is described in more detail in the paper. We hope that this work can inspire others to think of new ways of combining surfaces and spaces and 2D and 3D visualizations together in immersive analytics environments. Thank you for watching.